You're most welcome to this video. Today we are going to go through mechanisms under organic chemistry, and I've been requested by some of my followers to make a video of mechanisms. And today I begin with the mechanism of a carbonyl compound with an amine in presence of an acid. This one definitely in such questions begin by completing and writing the product, the main product you expect out of this reaction. This is a condensation reaction where we shall lose a water molecule in the reaction. So our mechanism, the mechanism we are going to follow is initiated by the acid itself, and we shall be commenting on some of the things that will be involved. So the carbonyl compound CH3, CH2, C, O, H. There is a lone pair of electrons on oxygen that is going to be attacked by the proton from the acid. The arrow begins from the middle of the lone pair, then is donated to the proton, so that we get CH3, CH2, carbon with OH, with a double bond that is now positively charged. Oxygen is already using excess of its electrons. Then it's going to receive a lone pair from the amine, because on the amine, the nitrogen has a lone pair of electrons to donate. The arrow comes from the middle of the lone pairs. So we donate it to the carbon carrying the functional group. And from there, our oxygen is going to be stabilized by breakage of a bond. So that will come up with a product which is CH3, CH2, carbon with OH. The hydrogen is spread out here, single bond, nitrogen, which is now positive. It has two hydrogens, but I'm breaking off one. I'm branching it off here, then NH2. What will happen is to stabilize the nitrogen itself by hydrogen proton shift, where this hydrogen will break off to stabilize the nitrogen, and the reaction that will occur will be a reversible reaction, which we call a proton shift. And with that, we shall form CH3, CH2, C. We shall have hydrogen, and we equally have OH2, which oxygen becomes positive with a single bond, NH, with a lone pair of electrons, then NH2. As the lone pair of electrons is donated to form a double bond, the condensation reaction will occur that allows loss of the water molecule. So on a complete arrow, we shall have loss of water for us to get CH3, CH2, carbon with only one hydrogen with a double bond that connects to nitrogen with a hydrogen, then NH2. This nitrogen becomes positive, and it's going to be stabilized by loss of a proton. That's why when we come to this, we shall say minus a proton, so that we form CH3, CH2, carbon, double bond, one hydrogen there, then N, and lastly NH, NH2. This mechanism or this reaction is going to be called a condensation reaction, simply because it involves this step, which is loss of a water molecule. So in condensation, we look at reactions that proceed with loss of water molecule. So since it involves loss of a water molecule, we shall call it a condensation reaction. Things to note is a proton shift or a hydrogen shift. This reaction here must be reversible. So if you use an irreversible arrow, we shall deny you marks. So that is the first mechanism that I was requested to comment about by one of my viewers. And the other mechanism is this, where our main product is not an alkene, simply because the alkyl halide we have is a primary alkyl halide with less than 3 carbon atoms. In this case, this use of this reagent cannot give you an alkene, but instead it gives you a ketone, which is ethoxyethane. So this is ethoxyethane. Before I write the mechanism, even if this one has been given in form of CH3, Cl, and I've added the same reagent, which is CH3, CH2, or negative K, plus in presence of ethanol, and I heat, this one will give me CH3 or CH2, CH3, so that it becomes methoxyethane. So that is how we can go about this mechanism. If we write the mechanism of this reaction, you're going to realize that our potassium ethoxide has to ionize to give us an electron-rich species and potassium. Ionization here is complete. Then, since it is a primary alkyl halide, it cannot undergo self-ionization. So the steps have to occur concurrently. This is hydrogen, this is chlorine, and this is hydrogen. I have CH3, CH2, or negative. Now here, everything occurs in a single step. As the electrons are donated to the carbon carrying the functional group, then chlorine will be allowed to go with its electrons. Watch movement of the arrows. In that case, we shall have CH3, CH2 added on oxygen with CH2 and CH3. So let us not forget about this mechanism, because I was actually requested to talk about it by one of my viewers. When I come to this, this is cyclohexanol, hexanol, X1 or cyclohexanol. Now, if I dehydrate it using concentrated phosphoric acid and I heat, I will definitely get an alkene. I'll get an alkene. And in my mechanism, the mechanism will begin with ionization of phosphoric acid. Since it is concentrated, ionization will be shown with a reversible arrow, and this will give us H2PO4 negative. Now, the alcohol OH has a lone pair of electrons, and it's going to be attacked by the hydrogen ion. After being attacked by a hydrogen ion, this is going to be donated. It's going to be donated to the proton, and donating it to the proton gives us, and it will give us this, where oxygen has 2 hydrogens bonded to it, and it becomes positive. Now, when you look at this, it has very many alkyl groups attached to it. So it can lose this water molecule first to have a loss of water before it gets stabilized. So this becomes a carbocation. And when I stretch out one hydrogen, the hydrogen is going to be attacked by the phosphate radical, where we shall have H2PO4 negative. The negative attacks the hydrogen, and this one comes, you make sure that it enters a little bit because we are forming a double bond, and this will give us hexene, which is an alkene. If I have this use of the same reagent like the one I've used here, the only difference is that here we are dealing with the primary alkyl halide, and when I take you to this one, we are dealing with a tertiary alkyl halide. So this one, the tertiary and a secondary alkyl halide, this one is treated with the same reagent, will give us an alkene. So my product is going to be CH3. I will remain with 2 carbon double bond, then the third CH3 will lose a hydrogen to form a double bond. My mechanism begins with the reaction between ethanol the reaction between ethanol and sodium hydroxide, which gives me CH3, CH2O, sodium plus water. Now, this salt here undergoes complete ionization. It undergoes complete ionization to give us CH3, CH2, O, which is negative, and sodium, which is positive. Now, the reaction, the mechanism begins with a self-ionization route, because we are dealing with an alkaline, tertiary alkyl halide, which can undergo self-ionization because of the stability gained by the carbocation, simply because the many alkyl groups have a higher positive inductive effect. So because of this, it stabilizes the carbocation. However, the reaction is going to be a partial arrow, a reversible reaction, which shows us self-ionization to get us CH3 in bracket 3, C plus, and then we shall also lose a chloride ion. Now this one, I'll try to break it a little. CH3, I'll remain with 2. My carbon, which is positive, single bond to another carbon that has 3 hydrogens. I'll split them and bring the electron-rich species to attack the hydrogen. As the hydrogen is attacked, it breaks off to form a double bond of the alkene, so that we can come up with CH3, 2 carbon, double bond, CH2. So that will become our mechanism in the final product. Thank you for watching. We shall continue making short videos to respond to our viewers. The channel remains Smart Science. I request you to subscribe, watch, and comment. If you have any concern, please you can send it through your comment or the comment section so that you can be responded to in the form of a video. Thank you for watching, and share the link to other learners out there to ensure that we can follow one another critically.